In this presentation, we're going to discuss solutions of polynomial equations. Now, we already alluded to this in section 6.0 in the algebra toolbox, if you will, but we're going to look into it in more detail. So, suppose that p of x is some polynomial equation, and then there's some x value equal to, let's say, a. When we plug in a into our polynomial equation, we get 0. Then, so if that happens, all of the following statements mean the exact same thing. They are equivalent. So notice I'm going to underline the really important vocabulary here. If p of a equals 0, that means a is an x-intercept of the graph of p of x, which means that the graph crosses the x-axis at a comma 0. That also means that a is a real 0. It's real, meaning that it's not imaginary. It's also a real solution to when we set the polynomial equation equal to 0. Even more so, x minus a is a factor of the polynomial p of x. So all of these things are saying equivalent, true statements based on just this one given. So some keywords: we get an x-intercept, a 0, a solution, and a factor, all when x equals a, because p of that value, p of a, equals 0. So again, I just want to highlight, we get a real solution, not an imaginary one, when p of a equals 0. Okay, so now let's kind of exploit and utilize these equivalent statements. So here, it's kind of like we have some polynomial equation that, let's say in factored form, was x minus 4, 2x plus 1, and x minus 7. Well, then we might want to know, when does p of x equal 0? So the same ideas hold true that we learned in quadratic equations. We're going to use that zero product property or zero product rule, depending on what textbook you look at. And remember, that reminds us that when a times b equals 0, that means either a equals 0 or b equals 0. Well, for this example, it's kind of like we're going to have an a and a b and a c. If a times b times c makes 0, a could be 0, b could be 0, or c could be 0. Any of those three terms must equal 0. So make sure you actually show your work writing out that x minus 4 could equal 0, 2x plus 1 equals 0, and x minus 7 equals 0. Now, these two solutions won't be tough to solve. But this one, some people might look at this and say, oh, so x equals negative 1. Actually, you have to be careful. That coefficient in front of the x term kind of makes things a little more complicated. So here's our three solutions. All right, let's keep on moving on. This, again, should feel like review from quadratics. But let's say we had a cubic equation, and we want to solve when does that equal 0. Always remember to look for the greatest common factor, which in this case is 4x. 4x times x squared makes 4x cubed, and 4x times negative 1 makes negative 4x. So always go further with factoring. We can actually factor out this difference of squares into x minus 1 and x plus 1. Now please do not forget that the greatest common factor is still part of this equation. Now we can use our zero product property or zero product rule. We can set 4x equal to 0. Divide by 4. 0 divided by 4 is 0, so that means x equals 0. Similarly, if we set x plus 1 equal to 0, we'll get x equals negative 1. Here we'll get x equals positive 1. So we have three solutions: x equals negative 1, x equals 0, or x equals 1. You can even have a greatest common factor. That's x squared, like in this example here. Every single term is a multiple of x squared. So we can factor that out and check and make sure everything's all right. And then we can even factor further to to get zeros if x equals 0, 1, or 2 by using that zero product property or zero product rule. Please be sure to show everything out. I know I'm skipping things a little bit, but I really expect to see x squared equals 0, x minus 1 equals 0, and x minus 2 equals 0. You need to show that you're breaking each of these factors up and setting them equal to 0. And then show the algebra out. Square root, so x equals 0. Add 1, so x equals 1. Add 2, so x equals 2. Because if you start to forget to show those steps, you're going to be missing crucial information. So here's not only an interesting word problem, but also another method of factoring that we haven't really touched on pretty much at all up until this time. So notice how we have a cubic function, but see how there's 1, 2, 3, 4 different terms when we write it in standard form? We're going to teach you a way to kind of factor, and this could actually work for things that have 3 terms, but you break up the middle term. But in general, we're going to use factoring by grouping with 4 separate terms. So the total cost of producing a product is given by this function. Who knows what the product is? But x is the number of units produced, measured in hundreds. So if x was 2, we'd have 200 units produced. And c is the cost, measured in thousands. How many units must be produced to give a total cost of 45,000? So it's important to recognize that that's a c value, or an output to this function. So we can plug in 45 in for c of x. And then if we subtract 45 from both sides, we have a cubic function equal to 0. And it's a cubic function with 4 terms. There's no greatest common factor. And so this is a little different than usual. There's no greatest common factor in terms of the entire c of x function. But here's the interesting thing. We can pull a greatest common factor from the first 2 terms, as well as a greatest common factor from the second 2 terms. So notice how we're kind of grouping these 2 together and looking for a GCF, and grouping these 2 together and looking for a GCF. And here's what's lovely. The first 2 terms share an x squared in common. The second 2 terms share a 3 in common. And then notice both x squared is a factor of x minus 12, and 3 is a factor of x minus 12. So we could factor out this greatest common factor, and then if you think about it, kind of like how when you multiply out 2 binomials, it's really just the distributive property. If we were to factor this up a little more, we have x minus 12, and it's a multiple of 3 from here, and it's a multiple of x squared from here. So we are actually able to factor this successfully, and this is factoring by grouping. Notice how the common factor was written out, and then the x squared and the plus 3 were written out right here. So factoring by grouping, it's kind of a neat trick, but every once in a while it can be very, very helpful. And then we can use the zero product property, and the only real solution would be x equals 12. If you were to solve by square roots here, x squared plus 3 equals 0. Subtract 3, you'd have x squared equals negative 3. Square root both sides, you're going to end up having a negative underneath the square root. That's going to be an imaginary solution, or solutions. So that's not a real solution, so that you can't have imaginary products that you're producing. So we must be producing 12, and remember that's measured in hundreds. 1,200 products will give us a total cost of $45,000 to produce. So there you go, a little factoring by grouping. And feel free to, Google this and seek other resources as well. So not always does factoring by grouping work. Here's a cubic where if you factor out the greatest common factor of x squared, you'll have x plus 2 left over. Here you factor out a 5, you'll have an x plus 3 left over. The x plus 2 and the x plus 3 are not the same, so we can't actually do factoring by grouping. So, there's a very interesting history behind factoring cubics, but factoring cubics is a tough thing to do. There's this cubic formula, but don't even worry about it. So factoring by grouping sometimes works, but it doesn't always work. And if it doesn't work, you're just going to want to really just go to your calculator. This root method is going to be very, very helpful and useful. If we have some equation of the form x to some number equals a value, for instance, x to the third power equals 9, or x to the fourth power equals 16, we can take the nth root. And so if we had x to the n equals c, we would take the nth root, that's a little n right there, the nth root of both sides, and then we'll have our one solution. But if n is even, so if the degree is even, when you take the nth root of both sides, you're going to incur this plus or minus, and we've already alluded to this. So you'll have two solutions in the end. You'll have x equals the nth root of c, and that's positive, and then you'll have x equals the negative nth root of c. So notice how you have those two solutions when n, the degree, is even. If c is less than 0 and you're trying to take the nth root on both sides, you're going to have no real solutions. You're going to end up with imaginary solutions. So we've already alluded to this nth root method, but it's very, very helpful. So now here's some practice problems. What I will ask you to do is do out all of the work on all of these problems. You'll notice that you have 3 questions followed by 3 answers. So you have to do the work to figure out that you are getting all of the correct answers. And notice in the nth root method in this example and these examples, we didn't say the imaginary solutions when we had, an even root that we were taking on both sides and a negative number underneath that root. So, for instance, you might have had some imaginary solutions. If you want, you could have them in this third question right here. But if you omit the imaginary answers, that's fine as well, because we really are only concerned about real numbers. So here's all the real solutions, and it's going to be a combination of all the methods that we looked at here today: factoring, looking for a greatest common factor, maybe factoring by grouping, and taking the root method. Keep in mind you might do more than one method in a specific problem, so make sure that you do all of the work and do these problems out for full credit.